Now I'd like to discuss the different types of proportional control that are possible. We don't simply have a choice of on-off and proportional control. In fact, proportional control is very rarely used on its own. It's usually used in combination with integral and derivative functions. And this is why our products are commonly referred to as PID controllers: proportional, integral and derivative. First, let's consider why proportional-only control isn't always the complete solution. Consider a controller with a proportional band nominally centred around the set point and adjusted for stable but responsive control. As the process rises through the proportional band towards the set point, the power output is reduced. Eventually, it will settle at the set point. If something was to cause the process to drop, the power output would be increased as the process fell back through the proportional band. This would bring the process back onto control. Similarly, if the process was too high, the output would be reduced as it rose through the proportional band. This sounds like it would work well, but in fact it would only work well if the output power required to maintain the set point was exactly 50%. In reality, this is unlikely to be the case. What would happen is the process would settle some way above or below the set point, and this would give us an offset. This offset, or control deviation as it's called, has to be removed by the user. An adjustment is made to the proportional band and its position relative to the set point. This is known as resetting the controller. However, if conditions change, perhaps the ambient temperature has increased, the user has to go through the process of resetting the controller again. They have to do this manually and may have to do it several times a day. The reason for this is simple. If ambient conditions have changed, then it may take more or less power for the controller to maintain the process at the set point. Similarly, in a hot water system, it may be that at certain times of the day, users draw more hot water from the process than they would at others, and therefore the percentage of power required to maintain the set point may be different. In each case, the users have to reset the controller. Integral action is combined with proportional control to create a PI controller. The controller measures the control deviation and tries to integrate this error out over time. Faced with a negative control deviation error, the integral action would bias the proportional band further upwards, increasing the power provided to the controller, bringing the process back towards control. At each subsequent run of the algorithm, further integral action will be added until the error has been eliminated. If some overshoot beyond the set point was to occur, the direction of the integral action would reverse. In this case, the integral action would bias the working point lower, reducing the power put into the process and starting to eliminate the positive error. So you can see that integral action is just doing automatically the reset function that the user had to perform with proportional-only control. And for this reason, it is sometimes referred to as automatic reset. We know that proportional control reduces the power as the process rises towards the set point. But if it's rising rapidly, there is a danger of an overshoot. Integral action will not help in this case. In fact, it would still be adding more power to the process because, although the process is rising rapidly, it is still below the set point. Only once the process has crossed the set point does the integral action reverse and start to reduce the power down. This is where we need derivative action. Derivative works on the rate of change in the process, either reducing or increasing the power if the process is rising or falling rapidly. Derivative action is not affected by where the process is or by the control deviation error. It is only affected by the movement of the process and its rate of change over time. Derivative action can be combined with proportional control to create a PD controller, or it can be combined with integral as well to create a PID controller. So if PID is the best form of control, why would you use PI, PD or proportional-only control? Some processes do not need the additional complication of a three-term PID controller, and it's possible that the integral and derivative functions can adversely affect the control in some cases. For example, derivative is known to cause premature wear in modulating valves. This is due to the excessive numbers of small movements in the valve due to the reaction of derivative to noise in the signal. In this case, the use of a PI controller is recommended. You may think that there's a heavy price premium to pay to get the benefits of PID control over proportional or on-off control. This is not the case. Virtually every controller from West is capable of full PID control as standard. The integral and derivative functions can be turned off if not required, and it's even possible to set the controller into on-off control mode if that is what you need.